understand why these systems work. Because for the most part, although there are all these amazing achievements, I think...
Thank you.
Great. Thank you. Although there are all these amazing achievements, I think there's really a dearth of deep understanding, and that will be very evident in some of these lectures, because I'm going to tell you a bunch of practical techniques that you should know about if you want to do machine learning or use it for your research. But in many cases, they're just ad hoc, and no one really knows why they work, and no one knows why you use that technique rather than another. So I'll tell you all the things that I know that do explain why things work, and there's some useful rules of thumb, but in many other cases, kind of no one knows. It's an open problem. It's like the success of machine learning itself is the data, and there's a lot to understand. I guess to belabor this a little bit more, it's a little bit like when we went from quantum electrodynamics, where Feynman diagrams perturbatively explain most of the phenomena we care about, to QCD, we really had to take a giant leap forward in order to understand strongly coupled physics. And I think you could think of machine learning as kind of like non-perturbative, strongly coupled statistics. Okay, so in this first lecture, I'm just going to give you a very quick kind of lightning overview of, I think, everything you need to know to sort of put the pieces together to understand what machine learning is doing. And then in the next two lectures, I'll go into more detail and tell you about some small selection of very specific techniques. And everything in these lectures is basically a small subset of a course on machine learning for physicists that I gave at Hopkins about a year ago. And so if you're interested in reading more about this, you can Google me and go to my teaching website, and somewhere on there is my course notes for this course. So basically everything I'm going to say is going to be a subset of that material. So, so what is ML at the most basic level? And what it is curve fitting with p much bigger than 1 parameters. So that's really all machine learning is. There are a lot of acronyms. There are a lot of different techniques. You may have heard of convolutional neural networks or recurrent neural networks or LSTMs, blah, 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 blah. There's all different forms of data, from the kind of data you care about to images, text, video, games, all sorts of things like that machine learning has been applied to. But at the bottom, every single machine learning algorithm, all it's really doing is curve fitting. And by curve fitting, I mean just this really dumb thing where you have some data and it's kind of noisy and it sort of looks like this. So I'm drawing a bunch of data points, and you try to find some function that goes through the data points. So maybe, yeah?
So what does it fit to when it completes your sentence, for example?
That's a great question, and I'll get there. So this, of course, is the familiar situation of curve fitting. Maybe you fit a third-order polynomial to a bunch of data points. All machine learning is doing this kind of curve fitting, but typically in a very high-dimensional space and with a huge number of parameters. So in ML, and this is sort of both true in practice and also it's advice to you, individual data examples are a high dimensional vector. And when I say vector, I don't mean necessarily in a mathematically careful, rigorous sense where it has certain linear properties. I just really mean a list of numbers with a lot of numbers in them. And so what would this list of numbers be? Well, just to start to address your question, if you have a sentence, you might associate a particular vector with every single word. Maybe you take a vocabulary of 50,000 words, and so there's a particular vector, say in a 50,000 dimensional space, or maybe 1,000 dimensional space, both come up, that represents each word. And you have a different vector for every word. And so then your sentence is the concatenation of, if your sentence has 20 words in it, it's a concatenation of 20 1,000 dimensional vectors. So that's one example of data. Another even more obvious example is if you have an image, it has some number of pixels. If you have a tiny thumbnail, which is 32 by 32, then you have 32 times 32 different pixels. If it's black and white, each of them has some grayscale value. If it's RGB, then each of them has 3 numbers associated with it. And so you can just flatten that out into one really long vector, and that might be your data. So if you have some problem that you want to apply ML to, and you think of the data as like one single number, probably if you're going to try to apply neural networks to it, you want to think of a way of kind of turning that one single number that maybe its precise values are important into a vector that's higher dimensional. So data is a high dimensional vector. And then what is a neural network? Well, a neural network at a basic level is sort of the simplest possible nonlinear function you could construct, given that your input data is a vector. So what's the simplest thing as a physicist that you would imagine ever doing with input data that's a vector? Well, I can take my input vector x, and I can act on x with some function f of x, which is some matrix wij xj. And if I want, I can make this affine, so I can add some constant to it. This is the simplest thing that you can imagine ever doing with a vector, is perform some linear or affine transformation on it. Now, this is just linear. It's not nonlinear. And what if I want to do something more complicated? Well, if I compose functions that look like this, I just get another linear function. If I compose a bunch of linear transformations, I just get another linear transformation. I'd like something slightly less trivial than this, so that when I compose f with more copies of f, I get something nonlinear. And so a thing I can do is I can write maximum of this, comma 0, for each component I. So this is really fi. And now I have a nonlinear function. So this thing, this maximum of this comma 0, in other words, this is something that is equal to this value when this value is positive and it's equal to 0 otherwise, is called a rectified linear unit in the machine learning literature, or a ReLU. So if you see that word, all it means is this function. This is really, in some sense, the simplest nonlinear function you can imagine. It's linear, and then it's 0 on every individual component of this. And this is the building block of basically every neural network that's in use today, is this kind of transformation. So I can compose these, so I can have, to be really explicit, I can have max of W2 ij of max of W1 jk xk plus B1 j 0 plus B2 I. So this function that I just wrote here is a 2-layer neural network. This would be a layer, and this is 2 layers because I composed 2 of them. Now notice W2 does not equal W1, B1 does not equal to B2. They're different parameters. So these things, W1, W2, and B1, B2, they're often called, people often use the notation theta, they're just commonly used. And these are neural network parameters. And again, there's specific terminology. So the W's are typically called weights. That's why they're W. And these are typically called biases. They're B. There's some intuition here that the W's are reweighting your data. The B's are biases in the sense that they're sort of shifts that determine whether or not your max function hit 0, where the max function hit 0. So that's the sense in which they're kind of like biases. But really, this terminology doesn't matter very much. It just, you'll see it all over the place, so I'm mentioning it. And these are your neural network parameters. So when I make this sort of 2-layer network this way, I'm taking my data and I'm hitting it with a function, and the neural network parameters define what function I'm studying. And so the goal in machine learning is to figure out what values these neural network parameters should take so that the function that I compute this way is useful for something. So in other words, probably the most vanilla example to ML people is image classification. My data X is some few thousand dimensional vector of pixel intensities, and I apply this function to it, and I like this function to output for me what the image is. So maybe there are 10 classes. The sort of simplest data set that you'll encounter and that sort of I would encourage you to play with is called MNIST. And it's handwritten digits. So it's things like 1, 2, 3, 4, and some of the 2s look like that, and some of the 3s look like this. But it's just pixelized images that are 28 by 28 of handwritten digits. And so a natural thing you can do is you can try to create a neural network that classifies whether this is a 1, a 2, a 3, a 4, etc. And so the output of your neural network then should be something like which digit I'm looking at. And how exactly to do that, maybe I'll tell you in more detail in a second. But that's the kind of thing that we want. And so what we're learning is the values of these matrices and these vectors. Now the other thing you can see immediately from this description is that there are going to be a ton of parameters. Because if my initial data is a image that's 28 by 28 or 32 by 32, then X is a vector whose dimensionality is order 1,000, and so W is a matrix with order 1,000,000 entries in it. And so right off the bat, I have sort of more than 1,000,000 parameters. Yeah?
But in this way, we can, let's say, put some words in W, and then reproduce a plain text, but only with that, are we able to reproduce poetry, let's say? I mean, to include metaphors.
The answer is yes. Not with this network with 2 layers that I just described, but something fancier. So probably tomorrow I'll tell you about, I think the most important paper from the last 2 or 3 years in machine learning introduced a neural network architecture called a transformer. And I'll probably tell you about that tomorrow because it's one of the things that you won't just instantaneously find on Google. That's the architecture that's used to do things like write poetry. And I mean, you don't have to believe me. I mean, you can play with this GPT-2 algorithm in a text box. You can see, I mean, it doesn't write great poetry, but maybe we don't either. So yeah. So this is really just the basic starting point. Now, so I just told you this matrix will immediately want to contain something like 1,000,000 parameters. Now, if I were to study a realistic image, like something you'd find on Instagram, then maybe that image is 1,000 pixels by 1,000 pixels, in which case X would be a 1,000,000-dimensional vector, and in which case naively W would be a 10 to the 12 parameter matrix. Now that's obviously a nightmare. We don't really want to have a matrix with a trillion parameters in it, and so a lot of the sort of work that's gone into neural networks, and it's really basic, is just figuring out clever ways of combining functions like this while avoiding having, say, 1 trillion parameters in a matrix and only having order 1,000,000 parameters in a matrix. And instead of having one matrix with 1 trillion parameters, we'll have, say, 100 matrices with 1,000,000 parameters, which will do much better. And so you've heard words perhaps like convolutional neural network, recurrent neural network, and I'll tell you about transformers. All of these are basically kind of simple, clever linear algebra tricks that take advantage of the structure in the data to not use quite so many parameters. Of course, they're still using millions or billions of parameters, but not, in most cases, trillions. So a lot of the sort of study of neural network architectures is just sort of how to be kind of clever model builders to build nice functions that account for, say, the symmetries of your data. And, for example, images are naturally translation invariant, right? I mean, the way that I see is the same no matter where I'm looking. I don't look, my eyes don't work differently when I look in this direction versus that direction, and I expect the world to have some translational invariance in it. Convolutional neural networks are an example that takes advantage of translation invariance to reduce the total number of parameters you need to have. Yeah?
Can you use ML to build such functions?
Yes, so people have tried that. I don't think it's actually worked that well, but there are tons of papers on it. So you can Google neural architecture search. I think there's maybe the best paper on this. There's a paper called Efficient Neural Architecture Search, which basically uses ML to iterate over architectures and try to find better architectures. I think only in limited cases is it done much better. For reasons that I can maybe go into at some point, but yeah. So part of the reason why I'm emphasizing that there's so many big numbers here, and I'm going to go through that in more detail later, is that we're obviously in some kind of thermodynamic limit here, in the sense that when you do curve fitting in examples that are familiar to curve fitting, there's like 3 parameters. Here there's millions or billions of parameters. And so I think this is another reason why this is a natural place for physicists to lend a hand, because these algorithms, quote unquote, are very different from ordinary algorithms that computer scientists study and prove theorems about. They're much more statistical as algorithms. Okay, so now I've just described some very basic way of constructing functions when your data is a high-dimensional vector, and this is what we use. The next question that we have to answer is, what's the goal of learning? So I'm going to break ML down into basically 3 questions. One is sort of how you define a function on the data. The second question is, what is the goal of learning? And this is actually the subset of ML that I think you can say the most about theoretically. However, at the end of the day, the things that you end up saying are very intuitive and kind of obvious. But this is the kind of thing that statisticians have studied for a long time, and so there's a lot of theoretical machinery you can talk about. Now, what is the kind of thing that you do? I told you that ML is just curve fitting. We now have this function. So something that I'm sure everyone has done is solve least squares. So we can write something called a loss function, which depends on our data and the neural network parameters theta. And so the simplest loss function is literally for regression, where the output of our neural network is not something even as complicated as which digit we have written in MNIST, but is just some real number y. And if our data is sort of x's comma y's, this is our data, then we can write a loss function L, which is, say, the sum over all of the data points of yi minus f theta of xi squared. So if we literally have regression, we're learning y as a function of x, then this is the kind of loss function you've probably just encountered. It's a very natural thing to write, and it's a loss function because big values of loss are bad, small values of loss are good, and so you just want to minimize this, and you're minimizing it, so we want to minimize with respect to the theta. So yi and xi are data, they're fixed, they're things that you actually have, they're facts about the world, and you're going to try to minimize this as a function of the neural network parameters theta. So this is the simplest possible example of what a loss function might be, and it just specifies a goal for learning. Now, in a lot of cases, you want to do something more interesting than just compute y as a function of x. For example, maybe you want to maybe you want a function that outputs which which digit I've written. Is this a 4 or is this a 9? It's possible I have really, really bad handwriting and that this is a 9, but probably it's a 4. Yeah?
Sorry, quick question. The smaller the loss is, the better is the fit, correct?
Correct, yeah. Yeah. So it's called a loss because you want to make the loss small. And it's just convention that in the field they usually want to talk about minimizing something instead of maximizing something. Yeah.
One question.
Yeah.
So, I mean, does this have to deal with overfitting and underfitting? How do you determine that?
Great. So that's a good question. I'm going to talk about it in a few minutes. Right now, I'm just ignoring it. This is something that you should absolutely ask about and worry about, and it's something that's surprising. There are surprising aspects of that in machine learning. So I'll talk about it in a few minutes. But if I don't, remind me. So sometimes you want to do something more complicated. I said that this is probably a 4, and when I say probably, you could then linguistically note that there's a notion of probability. In other words, I at least think about the world as when I look at the world and I sort of try to ascertain something, ultimately I think I'm making sort of probabilistic judgments. In other words, I say that this is a 1 and this is a 2 because I'm very, very confident. I have a very, very high probability for these being 1s and 2s, and a very low probability for them being any other digit, although of course there are some situations where I'm not really sure. So a natural thing our neural networks might output instead of a number like y as a function of x is a probability given x. So in other words, a natural thing to do when trying to classify whether I'm looking at a 0, 1, 2, 3, 4, etc., is I can have a neural network that outputs probabilities. And how do I do that? Well, in the simplest way, I can have my neural network output. I can first output, say, 10 real numbers. And then the second step can be, given 10 real numbers, there's an easy way of making those 10 real numbers into a probability, which is I can compute e to the xi divided by the sum on j of e to the xj. And this I can call my probability pi. So here I is, say, 0, 1, 9. And then I can, my pi is the probability that, say, what the image I'm looking at is one of the digits from 0 to 9. So this is sort of a very simple thing you can do to the end result of your neural network. You have your neural network first output 10 real numbers. This is called a softmax function in the literature. So if you see the word softmax, I mean, this is also just basically what you would do to have a Boltzmann distribution. But this is the terminology. I can learn these probabilities, and then I need to figure out what is my loss function if my output is a set of probabilities. If it's just a real number, then I can do this kind of naive curve fitting. But if my output is instead of set of probabilities, a thing I can do is I can do maximum likelihood. So what do I mean by maximum likelihood? Well, if my data consists of these digits as images, along with a label which says which image they actually are, then I just want to maximize the probability. I just want to maximize the probability of the correct label and minimize the probabilities of the other label, right? A good image classifier will say with 99% accuracy this is a 1, with 99% accuracy this is a 2, etc. So I want to maximize the probability. Now this is also something that may be familiar if you've thought about data analysis at all or statistics. This is something that we also do when we're trying to fit data. We try to some maximum likelihood estimation, and so this is a natural thing we can do. Now it gets a bit unwieldy to compute the maximum likelihood of a huge number of digits, right? If I have this sequence of digits, then what I would what I would output here is I'm interested in the probability that this is a 1, the probability that this is a 2, probability that that's a 3, the probability that's a 4, probability that's a 2, probability that's a 3. And the likelihood that I was right about all 6 of these digits is just the product of these 6 numbers. But they're all numbers between 0 and 1, and taking the product of a large number of numbers between 0 and 1 is not a good thing to do. So of course, what we do here is the thing that we do in all situations where you have the product of a lot of terms. We compute the logarithm. And so we want to maximize the sum of log of p label I given the image xi. Right? So the total probability that I was right about all of these 6 digits is this product. But I can just compute the log, and I want to maximize this sum. And so this is what we actually do in most cases in machine learning. In most cases in machine learning, we're not just computing a function, we're computing some set of probabilities. And the thing that we're learning is we're maximizing this, which means that our loss, because everyone talks about things in terms of a loss, is minus this. So in other words, you try to minimize minus the sum of the logs of the probabilities, where we take, say, an image xi, and we take the probability that it is, in fact, the correct label of that I. So this is the thing that's almost always used. It's used in image classification. It's also used in writing. So various people asked, how do you write, how do you figure out that, what does it mean for your function to output, say, a sentence? Well, typically you write the sentence word by word sequentially. And so what the machine learning algorithm actually does is the function looks at what words already are present, and it outputs the probability that the next word will be any of the, say, 50,000 words in its vocabulary. And so there might be 50,000 probabilities that are outputted, and we're just trying to learn neural network parameters that maximize the probability of the actual data.
Okay.
Yeah.
So in 2, you just define the number that's 0 and 1.
Uh-huh.
It becomes probability because of the way you define the likelihood. Like, how do I know that is actually probability?
Good. So, I mean, at a practical level, these are numbers between 0 and 1 that add up to 1. And so I'm going to interpret them as probabilities. If you start off with a neural network that knows nothing about your data, it will give you complete garbage. It'll just give you some random sets of numbers between 0 and 1. And as it learns, these will become better and better estimates of the probability of something that looks like probabilities. Now, there's an interesting question here. I mean, this is kind of a philosophical question. There are very, very different situations that you can be in. When you're classifying an image as, say, a dog or a cat, almost all of the time you're pretty sure whether it's a dog or a cat, or you're pretty sure whether I wrote a 1 or a 2. So the probability is kind of a silly thing because it's pretty clear that there's discrete categories. However, there are other situations, like if you're writing, then the next word that I'm going to say, there's a genuine uncertainty. Like maybe there are many words that are roughly equivalent that I could choose. Furthermore, you don't know my psychology. You don't know what I'm about to do. So there's really some statistics there. There's a lot of the probabilistic way of thinking about things makes more sense in some cases than in others. But we tend to use, in machine learning, people tend to use this same formalism, even when there's sort of a very discrete choice versus when there's a real smooth probability distribution. Okay, so this is typically what's used. A lot of what there's like a section or two in my course notes on machine learning, which is all about sort of statistics behind why you would use this and how you justify it. But at the end of the day, it's actually quite intuitive, and this is the answer. And so I probably won't talk about it during these lectures, just because I would rather save time for things that are harder to just sort of read about. But you could ask me about this at some point. Yeah.
Yeah, this PI that you define, this is probability of a particular digit being identified at that particular digit, right?
Yes.
But that takes into two parameters. One, how it is written, 2 in a certain way and it doesn't look like the 2 in some other way. So, but here it seems like it just takes into account one parameter, which is how you write it. It doesn't take into account the y parameter. Right?
Yeah, so what's good? So what's going on here is that
It's not supposed to sum up to 1.
so this is the probability for a given image that that image is a representation of a 0, a 1, a 2, etc. So really this is like a vector of probability, right? This is P0, P1, P2, P9. And these add up to 1. This is what I get. This is the output.
For a particular digit.
Yeah, this is the output of sort of f, maybe I wrote it as capital F theta of x for some given x, which is just an image. Yeah, and these add up to 1. And hopefully if your network is well trained, one of these is very close to 1 and the others are very close to 0. But maybe there's a really ambiguous digit, or maybe your neural network is not very well trained, in which case these might all be sort of a tenth or something like that.
Okay, so this works only for a particular label over here. The loss function that we defined as well.
Yeah, so maybe I use this notation without explaining it. So my data here is some set of images and labels. Here I wrote it as label of I. And so for each image, there is an actual label. So in other words, in order to train this neural network, you need someone to give you a list of images with the labels. If you only have the images without the labels, then you can't really do anything here.
Right. The only
Yeah.
the only point I'm a bit confused about is that label should be. It seems like you're summing up the labels as well. You're not summing up the labels. You're just summing up the xi's, right?
Ah, good. So the reason for that is that I don't really care so I'm maximizing. So I have this function that produces these probabilities, and I'm maximizing the likelihood that it's right about every case. I don't really care how it's wrong. So something you might have done is you might have said, well, if you're going, you might have said that like a completely reasonable thing that you might have asked is I could add an extra thing, which is P, I don't know. So if you wanted, you could try to train a neural network that says what the image is if it's pretty sure, but then it says I don't know when it doesn't know. So you show it a cat, it's been trained to classify digits from 0 to 9. You show it a picture of a cat and it says I don't know, and that might make you happy. And if you wanted it to say I don't know when it doesn't know, you'd need something more complicated than this because you need to sort of account for that. But here we're just assuming that every single image really is labeled, and so all we're trying to do is maximize the probability of the label we want, and we're not really caring if it gets it wrong, what it says when it gets it wrong. So yeah, if you wanted to do something like this, you'd need something else.
To continue kind of the point, is the output of L here is the same like there, or like it's a whole different way?
Well, this is a real number. Because these are logs of numbers between 0 and 1, they're negative, and so the loss is always positive. And a loss of 0 is perfect performance. Just like here, a loss of 0 is perfect performance, a loss of 0 here is perfect performance. They have quite different interpretations beyond that point, though. Like I said, there's a lot of statistics that can go into why you'd choose this, why you would choose this, how do you justify this. What if I have a prior? What if I have a prior that says that actually I'm almost certain that all of the images in my data set are 1s? However, it's possible they're not 1. How do I incorporate that prior? There's all kinds of statistics questions we can ask, but this is sort of the first lecture, and I'm trying to avoid all of these complications. Yeah?
Just to clarify, previously before you erased the point, you had the set of numbers, and for each number you had 1, so it had a P1, 2 had a P2.
Yes.
My question is whether for each element you check whether it can be all the elements. I mean, whether one can be 1, 2, 3, etc., or because you sort of pre-assigned an index.
Good. Yeah. So each image, produces. I mean, I'm not really doing this. So each image produces a list of numbers, which are all of these. But the loss function only cares about P associated with a label, which is, I think, what was being asked before. So the neural network produces all of the P's. And say you want to use your neural network. It's possible that you show it an image and it says 80% 2, 19% 3 and 1% all of the others. In which case you might say, oh, I'm really genuinely uncertain what the output is. Well, it says 80%, but I mean, things that are 19% likely happen some of the time. So the neural network produces all of these numbers, but the loss function only cares about the correct label when you're trying to train. So this is the thing that we're trying to minimize when we train our neural network. But training is just maybe the boring part. Once you have your neural network trained, then you can use it for stuff. And when you're using it for stuff, you care about all of these. Okay. Yeah.
So a neural network can be designed like it can give a probability of 80% whether it is 2 and maybe 90% if it is 3. So and in that case, the loss function would be more complex and.
Good. So when I say 80, I'm saying this is sort of not when you're training. So there's something fancier that you could have, which is your labels themselves could be probabilities, and then there's a different loss function that you'd use, which is called the cross entropy or the KL divergence. I can talk about that maybe in the next couple of lectures, but here I'm imagining that all of the labels are discrete and absolute. Okay, so. Great. So there are a few more comments I want to make about this, and then I'll move on to the sort of last thing you need to know to really just get started doing machine learning. So what losses are there that we're interested in? And we'd like to do a variety of different things with machine learning. The simplest thing we can do is something like classification, classifying images of 0, 1, 2, 3, 4, 5, or cat versus dog. But another thing that we can do is we can try to learn how to play games. And it's not at all clear how this is associated with, say, playing the game of Go, or playing Atari games, or something like that. Another thing you might want to do is you might want to generate an image. Well, what does it mean? I mean, this doesn't mean anything when you generate an image. When you're generating, say, images of fake faces, there are no labels associated with them. You're just making data up. So how do we think about this? Well, this is sort of this division in machine learning between supervised learning reinforcement learning, and what's called unsupervised learning. So these are three different categories. The category that we've talked about so far, both this and this, are representative of supervised learning. That's where the word supervision means that we know what the input is and we know what output we want, so we can supervise the network and tell it whether it's doing well and how it needs to sort of correct itself to do better. And that's the situation where we have these explicit targets. The other areas of machine learning that are equally interesting and important are areas where there's more distance between the data and what we want the network to do. It's harder, in other words, to specify the goal. And as it gets harder to specify the goal, learning becomes less efficient, and we have to sort of do more to figure out what we want to do. So you might be really interested in reinforcement learning because of things like Go and other games that are played. I mean, Go is something that, as physicists, it's a fairly nerdy pursuit, and so it's pretty interesting, and you might want to learn about it. I'm not actually going to talk about this almost at all because it's kind of its own subject. It would probably take up several lectures on its own. But the question is, in reinforcement learning, you have your data is, say, the game, which might be a game position. So in Go, it might be a position of a Go board. That's pretty easy to think about as data because you can just think of the Go board as a grid, and every square is either empty or has a white or black stone on it. So the data is pretty simple. But the output that you want, we want to predict the next move that we should make. And by predict next move, we want to be able to say what move you should make in order to win the game and do well. And that's true in Go. It's also true in Atari. In Atari, you say, see the screen of a game, and you'd like to predict how you should move the mouse or the joystick or something to win the game. This is also true in life. You're in graduate school learning to be a theoretical physicist, and you want to predict what's the next thing that I can do that will really, really impress the world and cause me to discover sort of a new theory of physics, a new theory of everything, and lead me to win the Nobel Prize. So this is a very, very broad class of problems. We want to predict, given all of our prior knowledge and experience, what the best next move is to optimize something. Yeah.
Has there ever been any sort of useful, not just for fun, reinforcement algorithm that someone used to sort of make real life decisions that people came to know about?
I mean, I'm sure the answer is yes. An example that comes to mind immediately, which is fairly bad, is I'm pretty sure it's public knowledge that YouTube uses reinforcement learning in part to try to figure out what video to show you next to cause you to not leave the YouTube website. So YouTube faces the problem. There's a human who's clicked on the following 7 videos recently in the last week. What video do I show them so that they'll watch it and stay? And what video do I show them after that so that they'll continue to stay? And I believe they're using reinforcement learning for that. They don't necessarily have to, but I've heard that they are. I think there are lots of other less sort of ambiguously great examples, but I don't know of any that are super famous. Yeah.
Do you have to, in that case, in the case of reinforcement, define the metric of what would constitute the next best move?
Precisely. So this is why this case is different from this case. If you'd already solved Go, then what you would do is you could use this, and you just say the best move to make now in Go is this one. But of course, you would have had to already solve Go in order to do this. So here there's a huge problem, which naively, when you first hear about this, seems insurmountable. It apparently, empirically, it's not at all insurmountable, which is that all you learn about when you play Go is like you make a bunch of moves, and then you have to figure out, at the end of the game, you either win or lose. That happens. But now you have, say, 200 moves that you made during this game of Go, and you lost the game. What do you learn from the fact that you lost the game? Do you know that move 19 was good and move 27 was bad? How do you possibly do that? How do you possibly figure that out? This is usually termed the sort of attribution problem. How do you attribute success or failure, your ultimate success or failure, to specific moves along the way? And this is naively a really hard problem. It's even harder when the time scale of the game becomes longer. So if you play a game for an hour and all you do is win or lose, then, and maybe you made a move every second or more often than every second. Like if you're playing Dota or StarCraft, which now have been won by machine learning algorithms, those games can go on for about an hour, and you make like 5 moves a second if you're a professional player, maybe more than that, like mouse clicks. And somehow you have to figure out which of those mouse clicks led you to win, which led you to lose. And this is naively a huge problem. It might feel insurmountable. It has been surmounted, apparently, empirically. I don't think that anyone has a theoretical understanding of that, in the sense that I don't think anyone could have told you ahead of time, if you only do machine learning in this way, you'll be able to solve this kind of game. I mean, I think it's an empirical fact that it's been solved. Yeah.
But the problem is that playing a game like a chess or a Go game, it depends also on the opponent that you have.
True.
Probably maximizing our profit, it is somehow equal to minimizing our loss, which does not mean that we have to win.
Yeah. So this is another added level of complication. Is there are other intelligent agents trying to utilize your mistakes to cause you to lose? You're not just playing against some fixed system. So this is also an additional complication in reinforcement learning, that there are these other opponents that you're playing against. So it's maybe the biggest lesson from Go and chess is that self-play has been very, very powerful. In other words, having algorithms play against themselves has been sufficient for them to get really, really strong. And because they have an incentive to figure out all of the different ways they can exploit themselves in self-play, that apparently leads to a very strong agent. So this is an interesting fact that self-play is very powerful. But really, this is all I'm going to say about reinforcement learning for these 3 lectures, and you can ask me about it or read about it. If you're really excited about this, I think maybe one of the best resources, if you Google spinning up on reinforcement learning, spinning up as in like spinning a hard drive up, there's a really, really nice set of lecture notes with like algorithms implemented if you're interested in learning about this stuff. But I'm not going to talk about it, mostly because it would take a really long time, and it's probably the least likely to be useful for physics research of all of these topics. Okay. And then there's this third area, which is usually called unsupervised learning. And naively, in some sense, this is the hardest, even harder maybe than reinforcement learning. Philosophically, unsupervised learning is saying, given the universe, understand it. So it's sort of the job of physicists. Given some data, understand the data. Now, what does understand the data mean? Well, a very nice way of sort of translating understand the universe into something slightly more precise is to say, can you compress the data? Because when you compress the data, you learn patterns and rules within the data that characterize it and differentiate it from just, say, random noise. So in other words, the laws of physics are an incredibly efficient compression algorithm for what happens in the world, right? Given some state in the world, if you know the laws of physics, then you can sort of figure out what's going to happen next. Naively, one moment and the next, if you don't know anything about the world, are totally unrelated to each other. But the laws of physics allow you to greatly compress that and tell you sort of what can and can't happen. And of course, machine learning is not at the level of learning the laws of physics from scratch, but that's the basic idea. Given, say, an image, or not one image, but a million images, what are the common features in all of those million images that can allow you to compress them into some set of features? And I mean, there are high-level examples that we're incredibly familiar with, like if you're looking at faces, is that person wearing glasses or not? Do they have long hair or short hair? Long hair and short hair are very, very abstract features or representations of faces that greatly compress a huge amount of information about the pixels in a particular image of a face into some high-level abstract concept. And that's the kind of thing that you would hope to get out of unsupervised learning. So there's this idea of compression. We would like to learn these high-level features that are characteristic of the data. So how do we actually do that? Well, typically in unsupervised learning, we make progress by basically turning it into a supervised learning problem. So one of the ideas that I just mentioned is compression. Compression is in some sense the same thing as a kind of understanding. When you've compressed the data, you've understood some of its most important features. Another thing that you can do to try to turn this into an even more precise problem is you can try to learn P of x, by which I mean the probability distribution of the data. So in other words, this is a weird way of thinking, but if you imagine all of the images that are on the internet, in some sense, you might imagine there's some probability distribution over images on the internet. Some images are very likely to appear, like images of attractive people on beaches are very probable on the internet, and some images are very unlikely to appear, like an image of random noise is probably really unlikely. I mean, maybe there are a lot of images of random noise on the internet, but nevertheless, a particular instantiation of random noise with random pixels is really, really, really unlikely. And so there's some imaginary probability distribution over all the images on the internet. Similarly, there's a probability distribution over all of the, say, text on the internet. Like certain kinds of language that's used in archive papers is common. Celebrity gossip and politics news are very common. Other things are presumably completely random juxtapositions of words are very, very uncommon. And so a thing that you can try to do, though it seems perhaps novel when you first hear about it, is learn that probability distribution. What is, given an image X, what is the probability that it actually exists on the internet? And that's really what you're doing in practice when you do unsupervised learning. So when you, for example, learn to write paragraphs and even write poetry, what you're doing is learning the probability distribution over existing text. And I'll mention it because it's turned out to be very powerful, and it underlies a lot of things that are in use now. Typically, the way you do this is via some kind of autoregressive decomposition of the data. So what does this mean? Well, an autoregressive decomposition of an image, I have this image that's divided into some grid of pixels. You just do that. In other words, you start out with a first pixel and ask, what's the probability that this first pixel will have some set of colors? Then you say, given that first pixel, what's the probability that the second pixel will have some set of colors? Then given those two, the next, and the next. Now this seems like a horrible way of decomposing an image. I mean, maybe the image has 1,000,000 pixels in it. Why would you want to go through pixel by pixel, these 1,000,000 pixels, and figure out, given, say, the first 500,000, what the probability that the next pixel will be this particular shade of red versus this particular shade of orange? But this is actually an extremely powerful method that's in use for understanding both images as well as text. Yeah.
But we can use the fact that you said that pictures are translation invariant, right? In order to see some patterns there. We don't have to go pixel by pixel, right?
So you don't have to, well, I would say many, I mean, there's some caveats. Many of the most powerful methods for doing unsupervised learning today use some autoregressive decomposition. Typically, if you really want to use, say, a huge image, then what you do is you first compress the image, taking advantage of some things like translation invariance, into something smaller, into some kind of code, and then you autoregressively read that code. But for text, this is literally exactly what you do. So if you want to write paragraphs, then you just look at all of the words you've seen so far, and you then predict a probability for the next word, and then you have that next word, then you feed it back in, and you predict the probability of the next word, etc. So this is something that's actually powerfully used for images, which is surprising. It's maybe less surprising for text because text has a natural autoregress. I mean, you really do read words one by one in a fixed order, so it's not so surprising you'd want to do this. But I just want to mention this because it's at least currently one of the most powerful techniques. Yeah.
I have one more physical question, let's say. Can we use any more symmetries on that picture? I mean, like scale invariance or even conformal scale invariance in a sense, to project it in another space, which is...
Yeah, absolutely. So historically, I mean, until the last couple of years, I think when people talk about images, they almost always talk about convolutional neural networks. And convolutional neural networks do absolutely exploit the symmetry, both translational. I don't know exactly whether they use conformal symmetry. I mean, but approximately they're at least using translational symmetry. Surprisingly, this is actually still very powerful. So when you use this powerfully for real images, like I said, you first use a convolutional neural network to kind of to take the sort of fine-grained features and extract them out and make them into some already more compressed form. But then you use this sort of autoregressive process to understand, to draw the image. I think the problem with using convolutional neural networks all at once is that then you sort of have to like make the image all at once, whereas this allows you to sort of break making the image into a lot of different separate pieces. I think that's sort of the intuition for why this works, but I don't really know. I don't think it is known in a clean way.
Excuse me.
Yeah.
So when a regression starts, it follows a pattern.
Yeah.
So this pattern is not translation invariant.
It is not. It's not.
So why a picture is translation invariant is important. I mean, it doesn't matter from where the regression starts. So the statement
Well, so I mean, the very first pixel, of course, doesn't really matter very much, and you can't really have a very good like, there's no a priori way in which this first pixel is very well determined. Once you know the first pixel, the next pixel over, there's a lot that you can know. For example, probably it doesn't differ that much. I mean, when you go from pixel to pixel, they don't really change very much. And then as you accumulate more and more and more, now your image you've broken the translation symmetry by fixing the first n pixels or whatever, and now what the next pixels will be in terms of the first is I mean, there's a lot of information about that if you know a lot about the data.
I mean, that's fine, but why it has a transition symmetry being matters?
Oh, well, I'm not, yeah. I mean, this is I think what the other question was about. When you use this autoregressive approach, you're kind of throwing out the translational symmetry. You're not taking advantage of it very much, which maybe is a mistake, but nevertheless, this approach works surprisingly well anyway. So if your data has some symmetry, it's sort of stupid for you to ignore it, but you can always just ignore it and treat the general case that doesn't assume that symmetry. So that's kind of what's going on here. Yeah, I mean, I mentioned the images in this case because, in some sense, it's surprising that it works so well, but it does. So this is what you're doing. So these are the three categories that you'll hear about. I'm not going to talk about this. This is playing games. This is things like classification. And this you solve by thinking about it in terms of compression and learning the underlying probability distribution of the data, and then by basically turning it into supervised learning. And I mean, maybe that's the point that I didn't drive home. Once you make this into an autoregressive problem, it's literally supervised learning because you have an image, which is, say, 1,000,000 pixels, and now you have a problem where you say, well, given 1,000 pixels, what's the probability that the next pixel is whatever? And you have the image, so you know what this pixel is, what this pixel is, et cetera, because you literally have a concrete image. And so this is now a supervised problem. Your supervision is the data about the pixels themselves. Okay. So, yeah.
In this assumption that your input data always follows a smooth probability distribution. Otherwise, why we should start looking for probability distribution?
Well, I guess there's not, I mean, formally there's no assumption that it's smooth. I mean, these probability distributions could be very, I mean, some of the probability distributions could be 1, 0, 0, 0, 0, et cetera. But yeah, I mean, it has the assumption that the data you're using somehow is drawn from a probability distribution. That is a weird assumption. It works very well. I don't think it's that weird. I mean, I think the thing that's weird about it is that really they're conditional. Like, the probability distribution of images on the internet is somehow related to the fact that, like, the world is populated by people with certain cultural backgrounds and with certain governments and things, and somehow ultimately that determines what this probability distribution is. If the entire world was fascist, maybe we would have different images on the internet. We would have different probability distribution, but you could still learn that probability distribution just from the data itself. Okay, so I want to emphasize now, we've talked about what functions we use, which are these neural networks where we have high-dimensional data, we hit it with matrices, we compute a nonlinearity, we hit it with another matrix, we compute another nonlinearity. We've sort of answered the question of what is the goal of learning. And the answer was learn the neural network parameters by minimizing the loss at the overview level, and these are three different ways that the loss can arise kind of conceptually that are all quite different. And then the third question is how to learn these theta. So in other words, concretely, you have a function that that's representing the thing you care about, which is this neural network. Could be another function, but we're using neural networks. You've decided what the goal of learning is, which is to minimize the loss. The loss could be something like as simple as least squares, or it could be a maximum likelihood optimization. And then there's this third question of, like, concretely, how do you figure out what parameters theta actually minimize the loss and give you good performance? And this is called optimization. That's just the word that's used for this kind of process. So how do we optimize the theta to minimize the loss? This is obviously crucial because if we can't do this, then we won't ever find a function that does what we want effectively. And so in practically, we use some form of gradient descent. Which means that we discretely update our parameters theta. So we have some theta of our n plus 1 value of theta is theta n, and in the simplest case, minus epsilon times d theta of the loss, which depends on theta and also on the data. So, I mean, these are all vectors, or, I mean, maybe to be more of a physicist, and in some ways clearer, there's some sort of theta I, and this is some ddi, or dd theta I. So this is the gradient descent approach, which is that we're trying to minimize the loss. So we start out with some random values of theta, and then we update our values of theta each time by some number epsilon. So this is usually called the learning rate, this number epsilon, times the derivative of the loss with respect to theta. And so we just keep taking these steps in order to try to minimize the loss. And of course, this is something that's very familiar in sort of some physics context. The loss, so this is, say, some theta, some value of theta, and this is the loss. And we're just taking discrete steps, etc., in order to try to minimize the loss. So, of course, if you're a physicist, if you haven't been thinking this way before, you should now. The loss is very much like the potential. It's like some potential energy. And you're trying to find the minimum of the potential energy. The potential depends on millions of theta parameters, which is sort of like having a potential for some many-body system that's classical, and that just depends on a huge number of different coordinates, and you're just trying to find where the minimum of the energy is. That's what this loss is. This is often called the loss landscape because, of course, it may not be this simple. It might have all sorts of different features, hills and valleys and nooks and crannies. This is just a one-dimensional way of thinking about it. And you're just trying to minimize the loss. So this is obviously a thing you can do to attempt to minimize the loss. So before I say more about it, one thing I want to mention is that usually this algorithm is called, usually the term you'll hear for this is SGD, which is stochastic gradient descent. So you know what gradient descent is, it's just this. Why is it stochastic? Well, you have some data set which, say, contains 1 million images. You could compute the loss summed over all 1 million images in your data set. However, that would be a huge amount of computation, but you have to compute the loss for every image, then take its derivative for every image, and compute the sum of those derivatives, or the mean of those derivatives, and that would give you your update rule. A much simpler thing you can do is use a batch of data, which might be, say, 10 to, 10,000 individual data points when you compute this loss. So instead of this loss being the loss for all of the data in your data set, which would be a huge pain to compute every time, you can just use a batch. Sometimes this is called a mini batch of data, which only contains, typically, this is a typical range that's actually used, 10 to 10,000 images in your data set. And that's why this is stochastic. That's what this word stochastic comes from, because you're not actually minimizing the loss. You're minimizing some stochastic, slightly randomized version of the loss, because you draw these, say, 1,000 images from your data set randomly. You just draw them randomly with replacement. And then you compute this, and you take a step, and then you compute on a different random draw of 1,000 images on the next step, and the next step, etc., in the hopes that this stochastic process eventually gets you to a good minimum, while also being much more efficient than using the entire data set at once. So that's what the word stochastic and stochastic gradient descent comes from. So this isn't literally what's used, but something very, very similar to this is what's actually being used in pretty much all of machine learning research. So I don't know if I should say more now or later. Let me make some comments. So in doing this, obviously, a major constraint here is computational efficiency. I mean, for example, that's one reason why you don't use the entire data set. Another thing that you might ask is, well, maybe there's some much smarter way of doing this. So, I mean, maybe I'll talk about this more. But for example, you could have used Newton's method, if you know what Newton's method is. Newton's method involves using not just the first derivative, but the second derivative of the loss with respect to the data. But the second derivative of the loss with respect to the neural network parameters. But the second derivative is like d squared d theta I d theta j of the loss. This is the Hessian. Newton's method uses the Hessian. But if there are 1 million neural network parameters, then this is a 1 million by 1 million matrix. If there's 1 billion neural network parameters, then it's even worse. In other words, this is some very, very big object. And Newton's method involves using H inverse times the gradient of the loss. That's what Newton's method, that's what the update is for Newton's method, if you recognize this. And taking the inverse of 1 million by 1 million matrix sounds like a horrible idea. And so that's one of the things that stops people from using things like this. So if you immediately think, oh, well, I can think of lots of much smarter ways of doing this, the main reason why people probably aren't using that smarter way you can think of is because of computational efficiency. Yeah?
So how can you deal with the complexity of the landscape in the sense that you can start with a random point and end up in some local minimum best optimal?
Absolutely. So I mean, these questions are very good. This is a very good question. I think roughly there's some sense in which no one knows the answer to this question. There's also the sense in which, I mean, this field, I'm sort of saying this field kind of started in earnest in really the last 10 years, but people knew about neural networks for a long time. One of the reasons I think why people were skeptical of them was exactly this question of like, if you do this, don't you just end up in some local minimum? How do you know that local minimum is useful at all, etc.? And this is a question that there's some empirical work on this, but I think people don't really know. So let me list lots of objections about this process, because there are other ones. So one of them is, don't we just find a local minimum? Relatedly, just generally, this is non-convex is the usual words that people say. Typically, the loss landscape as a function of the neural network parameters is not convex. Almost all of the theoretical work on optimization, this is something that's very well studied by applied mathematicians, is you can prove all sorts of theorems about convergence in the convex case. But naively, things are non-convex, and so you'll only find a local minimum. Somehow, empirically, this just actually doesn't matter very much. I don't think this is the number one problem that obstructs doing well at machine learning, but I don't think that people understand why. So I don't think I have anything very concise or interesting to say about it. Basically, it seems like the local minima that you find are actually quite good. Furthermore, another empirical thing is that typically the local minima are linked by lots of flat regions, and so you can sort of move around in the flat regions and do roughly equally well. There are lots and lots of things to say about this, but somehow this doesn't matter all that much. A problem that in practice matters more, I think, is ill conditioning. So what does ill conditioning mean? Well, you can have a potential, maybe you like this if you're, say, studying inflation. You can have a potential that's like very steep in one direction, but sort of very shallow in another direction. So this is supposed to be a representation where there's some valley, there's some very steep direction where you are going to very quickly find the minimum, but then like you're very, very slowly rolling down in this other direction. If you're building a model of inflation, slow roll is something that you want, but if you're trying to do optimization, you don't want that, because here in this direction the gradient will be very small, and so you're going to sort of very slowly make steps, and that means you're going to have to iterate this process a huge number of times. And I say ill conditioning is what matters because in this situation, it's the sort of difference in how quickly you learn in one direction versus another that ultimately matters. If all of the gradients are small, you can always just make your learning rate bigger and account for that. But a bad thing happens in this situation, which is that if your learning rate gets much bigger so that you learn quickly in this direction, then what will happen is you'll sort of explode out of the potential in this steep direction. And that's why ill conditioning is a problem. And in practice, I think it's like maybe the biggest problem. And I think it's also the reason why no one really uses literally this formula, this gradient descent formula. Instead, what's in use are the dominant algorithm that's in use is a sort of ad hoc modification of this that I'll talk about maybe in one of the other lectures. So people use an algorithm called ATOM. Again, ATOM is some sort of meaningless acronym. I don't even remember what it's supposed to stand for. So people use some other algorithm called ATOM, which in some sense is supposed to help with ill conditioning. In practice, it helps a lot. So if you're going to actually ever do anything with machine learning, I highly recommend you use this algorithm. I'll tell you what it is in one of the next two lectures. But no one knows why it's the thing that you should use. It's just an ad hoc thing. I should say it only uses information about the first derivative. So there are really not very many things that you could possibly imagine doing if all you ever use is the first derivative of the loss at any given point. And this is some clever thing that uses the first derivative to try to partially ameliorate this problem. There's another thing which is actually built into ATOM, which is called momentum. Momentum is like, instead of using the current gradient, you can use the mean of the last, say, 5 gradients as your update rule. And your hope in doing that is that like you'll sort of zigzag here, and so the gradient will cancel itself out. But in this direction, it'll add constructively, and so you'll sort of do a little bit better. And you can actually prove that in the case where you're just in some convex region, if you ignore this non-convexity, you can actually prove that accumulating gradients in this way leads to better performance. So that proof is on the internet in various places. But the thing that people really use is not just this accumulation of gradients called momentum, but ATOM, and no one has any theoretical proof that this is a good thing to use. But ill conditioning, I think, is the biggest problem that you face. There are a bunch of other points about the loss landscape. So one thing that you might realize quickly is there are a lot of degeneracies in the loss landscape, because you can permute the rows and columns of a bunch of different matrices in your neural network and get the same function at the end of the day. And that means that there are a huge number, like a factorial number of degeneracies in the neural network. That's just an interesting fact. Another interesting fact is that if you make up a random function, you might guess that roughly half of the eigenvalues of the Hessian locally will be positive and half will be negative, which means that there should be a lot of saddle points. That's an interesting observation, but I don't really know it doesn't necessarily really tell you very much about what to do. A third point is that the physicists thinking on optimization is terrible. What do I mean by that? So just the following. So I made this point that this is a lot like a potential. And so a thing that you might immediately think is, wow, I spend a lot of time studying, say, inflation models. I know a lot about how sort of balls roll down hills. And so this is going to be a great place for me to contribute. So what is the limit that you take as a physicist when you're thinking in that way? Well, you take the limit that the steps are tiny, and probably you also imagine, or I mean, if I draw this picture, I'm imagining the potential is fixed. So this is a terrible approximation in the sense that your goal in optimization is to get to the minimum as quickly as possible with as little computation as possible. You're paying a lot of money to use Google's compute cluster, and you want to pay as little as possible. That means that basically whatever the potential looks like here, you want to jump as far as you can so that what the potential looks like at the next point is almost uncorrelated with what it was before. In the infinitesimal, in the limit where your steps are tiny, the potential at the place you jump to is very, very, very correlated with what it was at your starting point, because you're sort of imagining that everything's smooth. But here you want the exact opposite limit, because if you jump to a point where you already knew what the potential looked like at the point that you've jumped to, you've wasted information. In other words, you used a bunch of GPUs to compute this gradient, and you want to use all of the information in that gradient that you can, and then in the next step use completely new uncorrelated information. So that means that the continuous limit, or the limit of sort of slow roll or smooth rolling here, is sort of the worst possible limit. You're wasting a lot of information. In other words, you want to take as big steps as you can, which means the discreteness of these steps really, really matters, and you should be in a limit where you can't ignore the fact that the steps are discrete. The other thing is that the stochastic part is also important. If you use all of the data, if your batch size is the full data set, then there's just one potential, and you can imagine moving in that potential. But here you're trying to be efficient, which means that there's going to be some real tangible noise due to the fact that you're not using the full data set. And that means the potential is actually a different potential on one step compared to the other. I mean, hopefully they average out to give you the full potential in some sense, but really there's a lot of randomness. The potential is fluctuating a lot in itself. So this is just sort of a warning. If I feel like some percentage of physicists hear about machine learning and they think, oh wow, like because I studied inflation models, I sort of know what people should do. You should at least keep these maybe counterintuitive facts in mind. Okay, so I think it's been an hour and a half. I think, let's see. I don't think I got as far as I expected, but it's not too bad. So I guess we'll stop here. This is a natural stopping point. Let me just emphasize, really all you need to know is this sort of organization of thinking, that the three things you need to determine before you get started are: what is the function you're going to use to represent the goal of what is the class of functions? We're studying neural networks, which are just made of linear algebra plus the simple nonlinearity. What is the goal of learning? It's to learn these parameters. There are a huge number of them. They're the elements of matrices and vectors. And then how do we learn these? We just do optimization using some variant of gradient descent. And if you're going to do this in practice, you probably want to Google what atom is, or wait for another couple of days, and I'll tell you. So I'll stop there. I'll continue probably with this sort of overview next time, and then hopefully we'll get to talking more about architectures so that I can tell you about the transformer. not sure what else, but if you have any very strong recommendations, I'm open to talking about whatever is most useful to you. Yeah.
At the very beginning here, we defined this rectified linear unit. And
Yeah.
This is certainly a very simple way of making a nonlinear function. But
Yep.
if I were just coming at this maybe from a more pedestrian point of view, the first thing I would do is put in a quadratic term or something.
Uh-huh.
So is there a reason why that doesn't really work as well, or is it just where there are certain classes of problems where it works better?
So that's a totally reasonable question and idea, and I don't know is really the answer for the quadratic thing, but I can tell you a couple of things. So, interestingly, one of the big ways in which historically people failed in this subject was that people wanted to imitate biological neurons, and so they had an idea that things should sort of be either on or off, and so they wanted to therefore use like the tanh function. So they wanted to use a function, in other words, that say looks like this as a function of its input. If you use this function, something bad happens, which is that there's some narrow range in which the derivative is significant, but for very small values or very large values of the input, the derivative is basically 0. So what that means is that there's a huge region in which you don't learn almost anything from, say, this update because the derivative is so small. So that was a problem. This is called saturation. It just saturates at 1 or saturates at 0. That was a problem in a lot of neural network research, was that they use this function. There's a related problem with the quadratic function that hopefully we'll talk about a bit, which is that you also don't want information, you don't want signals to blow up. So if you have a quadratic function, then if you're really using the quadraticness of that quadratic function, then as a function of x, your input is blowing up like x squared instead of like x. And a major problem, in fact, I think maybe the most important thing to know about architectures and neural network design is not convolutional or recurrent or the transformer I'll tell you about, but it's that you really, really don't want signals to either blow up or go to 0 as they propagate through your network. If you only have 1 or 2 layers, this isn't a big deal, but people now study networks with tens or hundreds. I mean, there are papers that study networks with thousands of layers. And if you have 1,000 layers, and every time your vector moves from layer to layer, it increases in magnitude by 10%, then you have 1.1 to the 1,000 by the time you get through the network, and that means that you're just going to get garbage, and you're not going to be able to learn anything. You can translate that into the statement that if signals blow up or decay as they propagate through your network, your loss landscape will be some incredibly horrible landscape. It'll have all sorts of bumps and crags and jagged pieces. And for optimization, you want a smooth loss landscape, which is the same thing as saying you want signals to sort of not be too attenuated or too divergent as they propagate. So I think that's probably the reason why a quadratic is not a good idea. People have tried other functions besides this ReLU function, but none of them do significantly better. And the ReLU is so simple, so people use it. Yeah. Yeah.
So I set up.
Oh, sure.
Just maybe in like 5 minutes.
Okay.
Finish up.
Okay.
And this food for everyone.
Okay, great. Thanks. Yeah. Sure.
So I mean, from the data thinking point of view,
Mm-hmm.
I know that people use the Monte Carlo to do that, and also try to use, for example, the Fisher matrix proposal to reduce the time matrix. But is Monte Carlo used for evolved by any chance in this case, in your network, or is it just too time consuming?
I don't know of almost any examples where it's currently being used, but in sort of machine learning stuff. I mean, I've heard of occasional situations, but I think it's not in mainstream use. I assume it's because it's not, well, so I'm not sure exactly what you have in mind. For optimization, like learning what theta you should use, people have tried things that are kind of like Monte Carlo, where you like, instead of computing the gradient, you sample lots of different values of theta, and then you sort of try to converge on a good value of theta just by randomly sampling. That doesn't work nearly as well as using the gradient, because, for reasons that I think are sort of next on my list of things to talk about, computing the gradient isn't very slow at all. You might worry that computing this gradient, if the network is complicated, is super complicated, but it turns out that this only takes about maybe twice as many floating point operations as just computing the neural network itself. And so since the gradient computation itself is cheap, you might as well use it. But yeah. Yeah.
You said one of the problems with the hyperbolic tangent function is you're not learning anything on the right and left limit where it's flat.
Yeah.
But the function you mentioned with the max of 0,
It's flat in.
it's flat on one side.
Yep.
Is that the problem?
Yeah, so that is. So people have thought, oh, that's a problem. So they've tried to use, so people call this a leaky ReLU. People have used a function that sort of looks like this. So it's like has some slope here. I mean, I don't think it empirically helps very much at all. But you're right that this does have this problem on at least one side, but at least it doesn't have this problem on both sides. Yeah. So, I mean, the state of knowledge about activation functions is just extremely poor. I mean, there are some papers that empirically study different functions and try to see whether they give different performance, and they always give sort of very, very similar performance. For, say, things like this versus the normal ReLU, people tried adding, like you could also try to solve this problem by making some function which is sort of like smoothly curves up or something, and it really just doesn't make much of a difference. But there's sort of no good theoretical understanding of this. Yeah.
So at the beginning you said that usually the people who address this are either from the engineer point of view or mathematics point of view.
Yeah.
And I remember like 1 year ago there was this paper that came out and he said about the mathematical part that it's usually sort of not what you really want, so it's really basic. But I remember there was this really, really interesting paper that was like, I don't know, 70 pages that seemed to prove a very general argument about generalization error in neural networks that have a much larger number of parameters than inputs. But then it was extremely complicated, and it seemed like at the time no one really read it. But do you think there are papers like that are like mathematicians wrote them, but they are useful?
So, I mean, there definitely are. I mean, I can give you a list. I mean, there are. I'm not definitely not saying that no paper that's ever been written is useful. The paper that I like best is actually written by, at least one of the authors was like a physicist, at least as an undergrad or something. There's this paper by Advani and Sachs. I think I referenced it in my course notes. One section of my course notes kind of goes over what they did. And if you read it, a lot of what's in their paper goes back to a paper by Jan LeCun from the 90s. Although he didn't he did a bunch of interesting math, and then he kind of didn't realize that it had interesting implications. This is one of my favorite papers in machine learning. I don't know that it's probably not the paper you're talking about, but it's a paper from I think 2017, and it explains something that I haven't really emphasized yet, which is in these neural network situations, you often have far more parameters than data. And that should seem shocking because, like, if you do curve fitting, if you have 3 data points and you have a 10th order polynomial, that seems like a horrible, like, what are you doing? You're just overfitting to your data. How could this possibly be useful? But neural networks are typically in the regime where there are more parameters than there are data points. And they give in this paper a very, very nice explanation of why that's not a problem. And so they theoretically sort of solve the case of linear models, and they show that for linear models that's not a problem. And in fact, there's something kind of like a phase transition which occurs when the number of data points you have is equal to the number of parameters you have. And having far fewer parameters or far more parameters is okay, but having almost exactly the same number of parameters and data points is bad. And they do some experiments showing that this phenomena is roughly true also in the nonlinear case. There's been a lot of work on that in the last year. There's a word associated with it, which is double descent. I think Advani Sachs deserve perhaps the most credit for this, although I don't think they get all of the credit. But people are sort of understanding this is true. So this is related to this question of generalization and overfitting, which I haven't talked about yet. So I think that's a good set of papers. There's a set of papers, some by a lot by physicists, because there's a lot of physicists now working on machine learning, about the large width limit of neural networks. So you take the limit that the matrices become infinitely big, and it's a bit like a large N limit, like in large N QCD. And there are a lot of nice things that happen in that limit. And there's a paper not by a physicist, but by, I think, mathematicians, called the neural tangent kernel, which is sort of a mathematical exposition sort of this limit, that explains why a lot of nice things happen and things simplify in this limit. So I think those papers are really good. And I mean, there are many others, but those are the first that come to mind. Right. Thanks.